So we would like to begin by addressing one of the issues that we discussed regarding how well the existence of partial derivatives replaces the notion of differentiability for functions of several variables. We easily understood that it is not a genuine generalization of the notion of differentiability, because a function, as we saw, may very well be discontinuous at a given point, but still have partial derivatives at that point. So it's a different aspect of differentiability that needs to be generalized in order to obtain a genuine notion of differentiability. And for that, let's recall one of the consequences of differentiability for functions of one variable. So we said that in the case of one variable, differentiability is pretty much equivalent to the existence of this limit that we call the derivative. Interestingly enough, this same limit can be written as, if we bring the f prime of a to the other side and clear denominators, we can rewrite this as f of a plus h minus f of a minus f prime of a times h over h is 0. And in some sense, we can express differentiability for functions of one variable by saying that f is differentiable at a if there exists a real number. Actually, here we should say if and only if. So that's precisely when it is differentiable. If and only if there exists a real number m such that the limit as h tends to 0 of f of a plus h minus f of a minus mh over h is equal to 0. And one could ask, okay, so why do we express the notion of differentiability in such a cryptic way? What's the meaning of all this? And the idea actually is pretty simple, that if we take our function and consider the expression of the function minus the value at the given point in terms of a variable h that allows us to distance ourselves a little slightly from the point A, then that difference can be approximated by a linear function in a very, very strong way. In fact, what one could have done here is even express this a little differently and rewrite this as f of a plus h minus, and in a parenthesis, we would have f of a plus mh over h is equal to 0. And here we might think of the function f of a plus mh. Please note that f of a and m are two constants. It's a linear function of h. And pretty much what we're saying is that our function, when we center it at a, can be approximated in a very, very strong sense by a linear function. So what is that strong sense? That when we take the difference between our function and the linear function, not only that difference tends to 0, that wouldn't be a big deal, actually. You could replace m by any number you like and you would still get 0 there. But you divide by h. Dividing by h is the same thing as multiplying by a huge number, and the limit is still 0. So in other words, one could intuitively say that differentiability is about being able to approximate the function at a given point by a linear function in a very, very strong way. And it's exactly this aspect of functions of one variable that we would like to extend and generalize for functions of several variables. And that allows us to come up with the notion of differentiability for functions of several variables. So let's see how this notion would unfold for a function of two variables. So we will say that the function f of xy is differentiable at AB if there exist real numbers u and v such that the limit as h comma k tends to 0, 0 of f of a plus h comma b plus k minus f of a b plus uh plus vk divided by the square root of h squared plus k squared is 0. Okay, let's try to demystify this expression that we just wrote and understand why this is in complete analogy with what we just stated for functions of one variable. So first of all, ask yourselves, what is this? This is pretty much a way to express f of xy in a way that it's centered around AB. So you start at AB, you add a small quantity h to a small quantity k to b, and this way, for small h and k, you obtain all the values of the function for points close to AB. Then, what is this? This is a linear function. It depends on h and k that has the same value as f of xy at the point AB. So we're pretty much saying that our function, the given function f of xy, can be approximated by this linear function in a very, very strong way. So not only their difference tends to 0 as h and k tends to 0. Again, this would have been pretty much the case for regardless of how you chose u and v. But you divide by the quantity square root of h squared plus k squared, which tends to 0, which means you multiply by a huge quantity and the limit is still 0. And it turns out that this condition provides us with a perfect generalization for the notion of differentiability. Because what happens now is the following. If f of xy is differentiable at AB, then it is also continuous, which is something that obviously we have in the case of functions of one variable, but we were missing if all we asked for was the existence of partial derivatives. And moreover, the partial derivatives partial of f with respect to x at AB and partial of f with respect to y at AB exist And can you guess what they are? And u is none other than the partial derivative, meaning the coefficient of h in that linear expression is the partial derivative with respect to x of f at AB, and v is the partial derivative with respect to y at AP. So, so the partial derivatives exist, meaning the notion of differentiability is certainly much stronger than the mere existence of partial derivatives. The existence of partial derivatives is implied. The only problem that one might detect here and might be a point of concern is, well, this definition seems a little hard to check. How can we ascertain that a given function is indeed differentiable? And in our course, we will not have a need, an explicit need to do this at any possible way. However, we should note that it's very straightforward to determine that we're dealing with a differentiable function by using the following criteria that says that if the partial derivatives exist and are continuous around AB, the partial derivatives of, let's say, a function f of xy, then f of xy is differentiable at AB. So what this says is that the only thing that you really need is that you have continuous partial derivatives. And that will be pretty much the case for all functions that we study in this course at points where they're defined. So we have a genuine generalization for the notion of differentiability that is actually very easy to check and confirm for all functions that anybody would be interested in using in our course. And regardless, we're going to leave this notion behind us, and it's a notion that we're not going to try to use at all after this point. But it's important for theoretical purposes to understand that what we're doing is in complete analogy with the theory of functions of one variable. And actually, one might say that the whole theory could have been developed for any number of variables pretty much simultaneously by giving the right definitions. And of course, that was the right definition for differentiability. We would now like to turn our attention to a different topic, which is a generalization of the chain rule. And again, we will realize that the role of the chain rule in the case of several variables is a little different than in the case of one variable. In fact, let's start by a generic case, because as we're going to see, it's very easy to present the formula for the chain rule. The only difficulty is that there is a bunch of different cases that one will have to think, but once you realize what the general pattern is, then those cases are pretty straightforward. And eventually, we would like to be able to understand what the deeper role of the chain rule in the study of functions of several variables is. So let's begin with the following situation. So imagine that you have a function f of xy, and the variables x and y can be expressed in terms of two other variables. So x is an expression of u and v, y is also an expression of u and v. So eventually, when you plug in those expressions into f, what you really get is a function of u and v. But here's the deal. Exactly because the function f from the get-go was a function of x and y, if you make this substitution, you really need to change the name of the function. And here you could call it something like g of uv. However, you will see that eventually we will drop the g and still talk about f of uv, which formally is an abuse of notation. In any case, what we're going to ask is the following question. What are the partial derivatives of this new composite with respect to u and v? So, in fact, we will be asking whether we are able to express these partial derivatives in terms of the partial derivatives of the old function f with respect to x, and the partial derivatives of x with respect of x and y with respect to u and v, as it would be expected from what is usually the case in one variable. And it turns out that yes, this is possible. And what we have is that the partial derivative of g with respect to u is simply the partial derivative of f with respect to x times the partial derivative of x with respect to u, plus the partial derivative of f with respect to y times the partial derivative of y with respect to u. And the expression for the partial derivative of g with respect to v will be completely similar. I would suggest that you actually pause the video and try to figure it out yourselves before you actually see what I'm going to write here. So this is what it is. The partial derivative of g with respect to v will be the partial derivative of f with respect to x times the partial derivative of x with respect to v, plus the partial derivative of f with respect to y times the partial derivative of y with respect to v. And yeah, that's what it is. Now, what is kind of interesting here is to eventually see how this formula, what this formula would become if we allowed ourselves the freedom of slightly abused notation, and instead of denoting this function here by g of uv, just call it f of uv. Again, formally this is not correct. Okay, but it's being done so often because people just don't want to have to use two different letter variables for pretty much the same function expressed in terms of different variables. So if that was the case, then you will be looking at the partial of f with respect to u being the partial of f with respect to x times the partial of x with respect to u, plus the partial of f with respect to y times the partial of y with respect to u. And the second formula, of course, would be the partial of f with respect to v would be the partial of f with respect to x times the partial of x with respect to v, plus the partial of f with respect to y times the partial of y with respect to v. And that would be the expression. And again here, one might actually, before we get to any example, can ask a few questions about the nature of these relations. So we have a sum of products, right? And where have we seen before such sums of products in this course? And the answer is in the case of a dot product. And we could be asking, is this a coincidence? And the answer is no, it's not a coincidence. But the truth is that if one wanted to give the more theoretical expression for the chain rule, one would have to go through matrices. And when we multiply matrices, what we indeed take is dot products between rows and columns. We're not going to try to look at this perspective, but it's important to understand that it is implicit in these considerations, and it is not just a mere coincidence. Okay, so once we have said all these things, it's important to give an example and see how this is applied. So let's take a look at the following example. So imagine that you have the function f of xy is equal, let's take a very simple function, xy squared, let's say. Okay, and now let's suppose that x is equal to u squared plus v squared, and y is equal to u cubed minus v cubed. Okay, u squared plus v squared, I meant here. And y is equal to u cubed minus v cubed. And I could ask the question, what is the partial of f with respect to u? In order to answer that question, we need to compute all these partial derivatives. So we will have the partial of f with respect to x is simply y squared. The partial of f with respect to y is equal to 2xy. The partial of x with respect to u is equal to 2u. And the partial of y with respect to u is equal to 3u squared. This should be sufficient in order to express the partial of f with respect to u. Because according to our chain rule, this will be partial of f with respect to x times partial of x with respect to u plus partial of f with respect to y times partial of y with respect to u, and we plug everything in and we get y squared times 2u plus 2xy times 3u squared. However, there is a small problem. I mean, the moment we entertain the possibility that we're going to leave the formula like this, there is something absurd. The absurd thing is that this formula has both x and y, which are the old variables, and u and v that are the new variables. And in some sense, that seems a little inconsistent, because initially you had a function of x and y, and now you want to replace x and y by their expressions in terms of u and v. So you would like to have a clean answer that contains only u and v, which means you need an additional step. And the additional step is simply to replace x and y by their equals in terms of u and v. So I will rewrite this as u cubed minus v cubed all squared times 2u plus 2 u squared plus v squared times u cubed minus v cubed times 3u squared. And that's a much better expression for the partial derivatives, for the partial derivative of f with respect to u by using just u and v. At this point, I would advise you to pause the video and try to find the corresponding expression for the partial derivative of f with respect to v. Okay, and certainly we're going to do it together. For that, we will need the partial of x with respect to v, which is equal to 2v, and the partial of y with respect to v, which is negative 3v squared. And we will have that the partial of f with respect to v is equal to the partial of f with respect to x times the partial of x with respect to v plus the partial of f with respect to y times the partial of y with respect to v. And this is going to be y squared times 2v plus 2xy times negative 3v squared. Again, we shouldn't leave it like that. We should try to express it using just plainly u and v. And this will give us u cubed minus v cubed all squared times 2v plus 2 u squared plus v squared times u cubed minus v cubed times negative 3v squared. And now we have the partial derivatives of f with respect to u and with respect to v. We would like to discuss some further examples here, but before we do so, there is a very important question that we need to answer. So one might argue that we used the newly introduced chain rule in order to find the partial derivatives of these functions. But one might ask, is this really indispensable? I mean, couldn't you just have taken the original function and write it in terms of u and v? How? By replacing x by u squared plus v squared and y by u cubed minus v cubed. And once you have written this, just take the derivatives with respect to u and v in the good old way. And the answer is an unavoidable yes. And all of a sudden, it seems that, okay, this rule has a certain theoretical significance. It might be interesting, but it doesn't seem to be indispensable, because we could achieve the same result just by finding the expression of our function in terms of u and v and taking the derivatives in a direct way. And the truth is that this is absolutely a possibility. But it would be wrong to say that the chain rule becomes redundant, because it doesn't. Before we produce an example that will show that the chain rule is anything but redundant, let's note how the chain rule is going to be presented in cases that the number of variables is a little different. And we need to understand that we can have a very flexible a lot of flexibility in considering different cases. For example, imagine the following scenario. You have a function f of x, y, z, and all of a sudden, it is given that x is a function of one variable t, y is a function of the same variable t, and z is a function of also the same variable t, which means that when you plug those into f of x, y, z, you get an expression that depends just on t. And now we would like to ask ourselves, how do we find the derivative of the new function of the excuse me, of the composite, if you will, with respect to t? And the interesting thing that one should take into consideration here is that, first of all, how do we write? We're not going to write partial of f with respect to t, simply because once you plug in the expressions of x of t, y of t, and z of t, we get just one variable. And this means that we should be writing the derivative by using the ordinary derivative notation, meaning the derivative for functions of one variable that has the upright d, not the curly one. So, so the chain rule will be what in this case? So we will have the partial of f with respect to x times dx over dt plus the partial of f with respect to y times dy over dt plus the partial of f with respect to z times dz over dt. And that would be the chain rule in this case. Okay, and basically what we're conveying through this relation is that whenever we express the chain rule, we have to be careful as to what is an ordinary derivative, meaning it's an expression that depends only on one variable, and what is a partial derivative, that is, it comes from an expression that depends on more than one variable. And here, obviously, f originally depended on x, y, and z, which dictated that these derivatives have to be written using the partial notation, but then x was a function of just t, which makes this an ordinary derivative, and so is this, and so is that. All three of them are ordinary derivatives, and also the derivative of the composite function is an ordinary derivative, which means that we use this notation. Okay, let's finish with one more example of how to express the chain rule in another setup. So let's suppose, for the sake of the argument, that we have a function of 3 variables now, and each of these 3 variables is an expression in 3 new variables. So x is an expression of UVW, y is an expression of UVW, and z is an expression of UVW. And we're asking what are the 3 partial derivatives of f with respect to the new variables u, v, and w. And at this point, you might want to again pause the video and try to figure out the answer yourselves before I write the answer. Here's the answer. The partial of f with respect to u is going to be the partial of f with respect to x times the partial of x with respect to u, plus the partial of f with respect to y times the partial of y with respect to u, plus the partial of f with respect to z times the partial of z with respect to u. Then we will have that the partial of f with respect to v is the partial of f with respect to x times the partial of x with respect to v, plus the partial of f with respect to y times the partial of y with respect to v, plus the partial of f with respect to z times the partial of z with respect to v. And finally, the partial of f with respect to w is the partial of f with respect to x times the partial of x with respect to w, plus the partial of f with respect to y times the partial of y with respect to w, plus the partial of f with respect to z times the partial of z with respect to w. And that's all. And that gives us, I hope, enough examples of how to consider the chain rule in any particular setup, along with the example where we applied the chain rule for specific functions. It should be enough of giving us a good idea about what this is all about. However, now we come to the most important part, if you will, of the whole discussion, which is why is the chain rule indispensable? Why do we need it when we always have the alternative of expressing our function in terms of the new variables and then directly differentiate that, directly find the partial derivatives? And here we're going to give a very interesting example. So imagine a setup in which the function that we're discussing is not a known function. It's an unknown function. In fact, that's the setup of a partial differential equation. A partial differential equation is an equation where the unknown is a function, and we have a relation between the function and its partial derivatives. Different partial derivatives may be of higher order. There's actually no limit on how diverse or complicated such equations could be. So imagine that you have such a situation, and for some reason, you're not happy with the variables that you're working with, and you would like to find the expression of the equation with respect to a different set of variables. In this case, you don't know what the function is. You cannot just find the expression of the function with respect to the new variables. You have to rely on something like the chain rule. And this is where we're going to give a very, very useful example. So in fact, we're going to look at the following partial differential equation. This is known, it's a very famous equation. It's known as the Laplace equation. And our task will be to express this equation using polar coordinates. Let's recall how to express Cartesian coordinates in terms of polar coordinates. So x is equal to simply r cosine theta, and y is equal to r sine theta. We recall that the way that they're related to each other is you have a point xy, and theta is the angle with the positive x-axis, and r is simply the distance from the origin. So r is equal to actually square root of x squared plus y squared. Okay, so what we would like to do is consider this equation, which is supposedly given for an unknown function or a function that is to be determined. And we would like to express it using polar coordinates. And the motivation for something like that could easily be that we just want to work over a domain which is very friendly to polar coordinates, let's say a disk. So why use Cartesian coordinates when polar coordinates render themselves to much simpler computations? So how do we take an unknown function that satisfies such an equation and translate the equation to another equation that involves partial derivatives with respect to r and theta? This is what we would like to explore right now. And let's see how this is done. So this is done by writing down the partial derivatives, actually second order, as we're going to see, with respect to r and theta, and trying to find a relation which is equivalent to the relation that we just gave, meaning the Laplace equation. So again, call this the Laplace equation. So let's see how this is done. The first couple of steps, when we're dealing with the first order partial derivatives, are especially simple, but you just have to pay attention to the steps that we take once we work with higher order partial derivatives. So let's begin with the partial derivative with respect to r. So the partial derivative with respect to r will be the partial derivative of f with respect to x times the partial derivative of x with respect to r. Okay, let's have this, plus the partial derivative of f with respect to y times the partial derivative of y with respect to r. And let's make our life a little easier. Let's use the subscript notation, which is a little more concise. So allow me to rewrite this as f sub x. And what is the partial derivative of x with respect to r? Remember, x is r cosine theta. So its partial derivative with respect to r is simply cosine theta, plus the partial derivative of f with respect to y times the partial derivative of y with respect to r, which is simply sine theta. And here again, somebody might want to understand in what sense we write such a relation if, for example, we knew what the function is. And the idea is simply that f is a function of x and y. Its partial derivatives with respect to x and with respect to y are also functions of x and y, and we replace those by expressions in terms of r and theta, meaning you would replace x by r cosine theta and y by r sine theta. So what you're looking at on the right-hand side would be completely an expression in terms of r and theta. And how would you do that for the partial derivative with respect to theta? Again, it might be a good idea for you to pause the video and try to get the expression by mimicking what we just did in the case of r. So what will it look like? Partial derivative of f with respect to x times partial derivative of x with respect to theta plus partial derivative of f with respect to y times partial derivative of y with respect to theta. And this will be f sub x times now, what is the partial derivative of x with respect to theta? That would be minus r sine theta. R is constant in this case, and the derivative of cosine theta is negative sine theta, plus f sub y times r cosine theta. Okay, great. So as we said, this was not that hard. What becomes much more interesting and much more possibly challenging is to see what happens when we take the second order partial derivatives. So in particular, I will want to take the partial derivative with respect to r twice, and the partial derivative with respect to theta twice. So let's start with the partial derivative of f with respect to r twice. Now, what's the logic here? The logic is that the partial derivative of f with respect to r twice is really the partial derivative with respect to r of the partial derivative with respect to r. But we know what the partial derivative with respect to r is, right? It's what? It's this whole thing, right? So what I have to do is take the partial derivative with respect to r of this expression of f sub x times cosine theta plus f sub y times sine theta. Now the question becomes, how do we take the partial derivative with respect to r of this? Now, this is again where things become kind of interesting. First of all, notice that cosine theta, as far as r is concerned, is a constant. And sine theta is also a constant. So what you really want to take here is simply the partial derivative with respect to r of f sub x times the constant cosine theta plus the partial derivative with respect to r of f sub y times sine theta. Okay? We need one more step here. What is the step that we need to take? Ask ourselves, what is the partial derivative with respect to r of f sub x? And now, here comes the interesting part, right? Ready? Well, we know the expression for the partial derivative with respect to r for a function f. Here, we don't want to take the partial derivative of f. We want to take the partial derivative of f sub x. So guess what? In this expression that I just circled, we should replace f by f sub x first, and then by f sub y, and see what comes up. And this is where it becomes kind of interesting, because look, here's what I'm going to do. Where you see f in that circled expression, I would put f sub x. So if I replace f by f sub x, think about it. For example, I will get f sub x, right? Which means I will get f sub xx twice times cosine theta. And then I will get f sub xy times sine theta. And the whole thing is multiplied by cosine theta. Okay, this is precisely the point where you should pause and think about it. Think about how we replaced f by f sub x and obtain these second order partial derivatives. And then similarly, we will have for the partial derivative of f sub y, we will have f sub y x times cosine theta plus f sub y sine theta, and the whole thing is multiplied by sine theta. And if you like, you can rearrange this slightly. So you will have f sub xx times cosine square of theta. And then remember that f sub xy is the same thing as fy sub x. That's Clairaut's theorem. So you will have two of the following things: f sub xy sine theta cosine theta plus f sub yy times sine square of theta. So this is the second order partial derivative for f with respect to r twice. Okay, now I would suggest that you pause the video and try to do something very similar for the partial derivative, the second order partial derivative of f with respect to theta twice. Let me warn you that it's going to be a little more complicated because you will see that you will also have to apply the product rule. However, it's quite worthwhile to try to do it yourselves before you play the video and see how it's done for the second partial derivative of f with respect to theta. Please understand that in this case, what you will have to use is this relation, this expression, exactly the way that we use the one which is circled in black for the partial derivative with respect to r. Okay, so let's take a deep breath and do it. So the partial derivative of f with respect to theta twice will be the partial derivative with respect to theta of the partial derivative with respect to theta, right? And how much was that according to what we had seen? It was equal to the partial derivative of x times negative r sine theta plus the partial derivative with respect to y times r cosine theta. That's what we had found. And now we are supposed to take the derivative of this with respect to theta. But here's where it becomes interesting. Now, each of these products really depends upon theta. I mean, in the previous case, we were sort of lucky. We had something, we had cosine theta and sine theta, and none of them depended upon r. But now, each of these factors depends on theta, which means that we have to use the product rule. So this is going to be what? For the first one, it's going to be the partial with respect to theta of f sub x times the second one, which is negative r sine theta, plus f sub x times the partial derivative of the expression negative r sine theta with respect to theta. And how much is that? That's negative r cosine theta. Okay? And then we need to do it for the other product. So we will have the partial with respect to theta of f sub y times r cosine theta plus f sub y times the partial derivative of r cosine theta with respect to theta, which is none other than negative r sine theta. Okay? Now, all we need to do is find these two expressions in exactly the way that we did it for r before. Okay, so what is that way? I mean, that way is we need to consider this expression right here and replace f by first f sub x and then by f sub y. And that is going to give us the expression that we're looking for. Well, let's do it. So this is going to be f sub xx times negative r sine theta plus f sub xy times r cosine theta, the whole thing multiplied by negative r sine theta, plus f sub x negative r cosine theta, plus, and now let's do it for the second component. So we will have what? We will have f yx negative r sine theta plus fyy r cosine theta times r cosine theta plus f sub y negative r sine theta. Here there are some simplifications actually that we can make. So first of all, let's multiply out. So we will have f sub xx times what? You have negative r sine theta times negative r sine theta. So that will give you r squared sine square of theta. Okay. And then you have this product and also this product that, if you pay attention, they're going to give you the same thing. Exactly because fxy is the same thing as fyx. And what is that thing? It will have a negative sign in front, so it will be minus 2 f sub xy times r squared, and then you have both sine theta and cosine theta. And then you have finally the one that has the second order partial derivative with respect to y twice, which will be fyy r squared cosine square of theta. Okay, and please note that I have left behind these two terms now that I need to account for. And there is something fun about these two terms. Let's think about it. It's I can factor out a minus r, and if I factor out a minus r, what do I get? I get f sub x times cosine theta plus f sub y times sine theta. And you may ask yourselves, have you seen this before? And the answer is, you sure have. If you go to the notes that you kept, you will see that this is none other than f sub r. Okay, it's f sub r. So I think it's now time for the grand finale. And to get the grand finale, what we need to do is get the expression for the second partial with respect to r that we found before and multiply it by r squared, because we're going to see something really interesting happening in front of our eyes. So we're going to get r squared f sub xx cosine square of theta plus 2 r squared fxy cosine theta sine theta plus r squared fyy sine square of theta. And now we have a small miracle here. I mean, you have to see that many things have to go right here, but it's such a nice harmony of relations. And let's enjoy this, because what I will want to do is pretty much take the expression for this and the expression for that and add them up. And here's what is going to happen. So first of all, look at this term. It has a negative sign in front, and it's exactly the same term as this, right? So this thing and that thing will cancel each other, right? So that's the first thing that we need to realize. And now, take a look at what will happen with this thing and this thing. When you add them together, r squared fxx is a common factor. And then what you get is sine square of theta plus cosine square of theta. Oh, the Pythagorean theorem tells us that this is 1. And finally, when you do the same thing for this one and that one, you will also get r squared times fyy. And of course, you will also have this last expression that will be there. So to make a long story short, if I take the partial of f with respect to theta twice, and I add to it r squared times the partial of f with respect to r twice, then what I will get is r squared fxx plus r squared fyy minus r times f sub r. Okay, and that's a little miraculous relation. Let's actually rewrite it on the other page in order to appreciate it. So we will have the partial derivative of f with respect to theta twice plus r squared times the partial derivative with respect to f, the partial derivative of f with respect to r twice. And then I bring over from the other side this r times the partial derivative of f. Let me use the Leibniz notation. So r times f sub r. And what this is equal to is r squared times fxx plus fyy. Remember that this is exactly the expression on the left-hand side of the Laplace equation. This tells you that a function satisfies the Laplace equation if and only if it satisfies this equation. So what we get is, and let's write it using the subscript notation, f theta theta plus r squared frr plus r times fr is equal to 0. And that's the Laplace equation in polar coordinates. And please remember that we didn't know, we never knew in this computation what the function f was, and the chain rule became the main tool in expressing the second order partial derivatives or finding an expression that would give us the equivalence between the Laplace equation and an expression that involves the partial derivatives with respect to r and theta. So I hope that this was a very convincing example that shows you how indispensable the chain rule is, that it's not something that just happens to be a tool that we can use if we're not in a mood to take the explicit composition of a function with some expressions of the variables. Instead, it's a tool that allows us to do things like that in a situation where the function is unknown. And that's just one of the things. There is much more to the chain rule than what one can express in a simple example like that. But I hope that this is an indication of how important the chain rule is. And that's all. Thanks for watching.